Good morning, everyone. Today we are going to be discussing about the biosynthesis of heme. That is, it is the integral part of heme metabolism. What is heme? Heme is the non-protein porphyrin compound, which are cyclic compounds which consist of 4 pyrrole rings which held together by methynyl bridges. Now, you see this structure, we can easily understand that these pyrrole rings are held together by the methynyl bridge and it is forming a closed ring structure. So, the naturally occurring porphyrins which contain a substituent group which is replaced the 8 hydrogen atoms of the porphyrin nucleus. This structure was put forward by Hans Fischer and it is called as Fischer projection of Fischer ring structure. The father, Hans Fischer, who is considered to be the father of porphyrin chemistry, who proposed the shorthand model for the presentation of porphyrin structures. According, each pyrrole ring is represented as a bracket. Thus, porphyrin has 4 closed brackets with the 8 subunit position numbered as shown below. So, what is so-called heme? Heme is the most important porphyrin-contained compound. It is primarily synthesized in the liver and erythrocyte-producing cells of bone marrow, that is erythroid cells. Heme synthesis also occurs to some extent in other tissues also. However, mature erythrocytes which is lacking mitochondria is a notable exception. So, as far as this biosynthesis of heme is concerned, it has 5 important stages. One is the formation of delta amino levolunate. Second is the synthesis of porphobilinogen. Third is the formation of porphyrin ring. And fourth is the conversion of uroporphyrinogen 3 to protoporphyrin 9. And fifth is the synthesis of heme from protoporphyrin 9. So, now we discuss one by one each. So, first step is the formation of delta amino levolunate. For the effective synthesis of hemoglobin, glycine is involved here. You know about glycine. Glycine is a non-essential amino acid. That non-essential amino acid or simplest amino acid glycine, which condenses with the succinyl-CoA. Succinyl-CoA is an intermediate in the citric acid cycle, or which are considered to be the starting material for the porphyrin synthesis. Glycine combines with the succinyl-CoA to form delta amino levolunate. This reaction is catalyzed by the pyridoxal phosphate enzyme delta amino levolunate synthase, which occurs in the mitochondria. So, this is a mitochondrial reaction. Here, this delta amino levolunate synthase is considered to be the rate limiting or rate controlling enzyme. So, here succinyl-CoA condenses with the glycine in presence of the enzyme delta amino levolunate synthase. Here pyridoxal phosphate is a coenzyme which can form a intermediate. That intermediate is alpha amino beta keto adipic acid. Thus, it can form delta amino levulinic acid. The second step, that is synthesis of porphobilinogen, when 2 molecules of delta amino levolunate condense to form porphobilinogen into the cytosol or cytoplasm. This reaction is also catalyzed by a metal zinc containing enzyme delta amino levolunate dehydratase. It is sensitive to inhibition of heavy metal such as lead. Now, the third step is the formation of porphyrin ring. Porphyrin synthesis, which occurs by the condensation of 4 molecules of porphobilinogen. The interaction of 2 enzymes, that is porphobilinogen 1 synthase and uroporphyrinogen 3 co-synthase. It forms uroporphyrinogen 3. That is the third step. So, thus it can form a closed ring structure. In the fourth step, conversion of uroporphyrinogen 3 to protoporphyrin 9. This is catalyzed by the series of reaction. One is by the involvement of by the uh, help of the enzyme uroporphyrinogen decarboxylase, which decarboxylates all the 4 acetate group present in the ring and side chain to form methyl group, which produce the coproporphyrinogen. Coproporphyrinogen oxidase, which convert 2 of the propionate side chain, that is vinyl group and propyl group. These 2 groups will be replaced here. As a result, to form the protoporphyrinogen and protoporphyrinogen oxidase methylene group, which interconnecting pyrrole ring to form methynyl group. This leads to the synthesis of protoporphyrin 9. Now the final step, last step, is the synthesis of heme from protoporphyrin 9. In these reactions, the incorporation of ferrous ion Fe2 plus into the protoporphyrin 9 ring, which is catalyzed by the enzyme ferrochelatase or heme synthase. Thus, heme is normally being synthesized in the body. In the system, it has 5 distinct steps. Each steps we discussed in detail in the above schematic representations. Now we have to be discuss about the disease states of heme synthesis. Defective enzymes may lead to some of the inherited diseases. These diseases are normally we can call as porphyriasis. Porphyriasis is a metabolic disorder of heme synthesis characterized by the increased excretion of porphyrin or porphyrin precursors. Porphyriasis, there are 2 types. One is erythropoietic porphyrias and there is hepatic porphyria. Erythropoietic porphyria, which is related to the enzyme which defect in the erythrocyte, and hepatic porphyria, the enzyme defect lies in the liver. We can see there are 5 diseases normally been there. Of course, we can consider hepatic as 4 and erythropoietic as 2. Hepatic porphyria, in this type, acute intermittent porphyria, which is defect of the enzyme uroporphyrinogen 1 synthase, which can cause the symptoms like abdominal pain, neuropsychotic symptoms, etc. Porphyria cutanea tarda, this is a second type, which is related to hepatic system, caused by the defect of the enzyme uroporphyrinogen decarboxylase. The main symptom we can find is the photosensitivity. Hereditary coproporphyria, which is caused by the defect of the enzyme coporphyrinogen oxidase, which may cause abdominal pain, photosensitivity, neuropsychotic symptoms, etc. And the last one in the hepatic system is the variegate porphyria, which is caused by protoporphyrinogen oxidase. Characteristic of this disease is the abdominal pain, photosensitivity, and the same as the above the neuropsychotic symptoms. And the erythropoietic porphyria, there are 2 types. One is the congenital erythropoietic porphyria, which is related to the defect of the enzyme uroporphyrinogen 3 co-synthase, which may also cause photosensitivity. And protoporphyria, which is caused by the defect of the enzyme ferrochelatase, most of the symptoms is the photosensitivity. Now we have to discuss how the synthesized heme being degraded, that is otherwise what we call as the catabolism of hemoglobin, heme. Okay, as a result, the end product of heme degradation is so-called bile pigments. Erythrocytes have the lifespan of 120 days. At the end of this period, they are removed from the circulation normally. Erythrocytes are taken up and degraded by the macrophages of the reticuloendothelial system in the spleen and liver. The hemoglobin is cleaved into protein part and globin and non-protein part heme. About 6 gram, approximately 6 gram of hemoglobin per day is broken down and which may be resynthesized in an adult human being having 70 kg body weight. The fate of globin is the globin may be reutilized as such for the formation of hemoglobin or which may be broken down into individual amino acids. Which are the sources of heme? It is estimated that about 80% of the heme that is subjected for the degradation comes from the erythrocyte, and the remaining 20% comes from the immature RBC, myoglobin and cytochromes. If you see the degradative pathway, if you see the aged erythrocytes that is reaching the macrophages, there it broken down to amino acids, and these amino acids normally been degraded further, which may be turned to each individual amino acid. And the other part, that is heme part, which consists of the central iron as the central metal atom, and it has the porphyrin ring, closed porphyrin rings with the methylene bridges, and having the attached group of methyl group, vinyl group, methyl group, vinyl group, methyl group, propyl group, and propyl group, methyl group. So that closed ring structure get broken by the enzyme heme oxidase. Thus, it can form biliverdin. So, biliverdin is the oxidized product of heme. This biliverdin get reduced by the enzyme biliverdin reductase. Thus, it can form bilirubin. So, bilirubin is the reduced product of biliverdin. That reaction is catalyzed by the enzyme biliverdin reductase. Thus, bilirubin is transported to blood through the circulatory system. In the blood, this bilirubin binds with the albumin, that is a simple protein. Thus, it can form bilirubin-albumin complex. From the blood, this complex is transported to liver. There, it binds with the UDP glucuronide by the help of the enzyme bilirubin glucuronide transferase. Thus, it can form bilirubin diglucuronide. This bilirubin diglucuronide now transported to intestine or kidney for excretion. There, it binds with the microbial enzyme, that is intestinal microbial enzymes, which forms urobilinogen. That urobilinogen is converted to urobilin. Through the urine, that urobilin get excreted. And urobilinogen is acted by microbial enzymes present in the feces, that is converted to sarcobilin, thus it is excreted. So, this is the synthesis and degradation of hemoglobin. Thank you. Okay.